good day. Today we will tackle structural analysis under statics of rigid bodies. Now, before diving into the video, it is expected already that you guys have a good background on equilibrium of a particle and equilibrium of a rigid body. Basically, it means that you should know the equilibrium equations, such as equilibrium summation of forces is equal to 0 and summation of moment is equal to 0. And if you guys have that background already, let's dive in. At the end of this lecture video, you guys are expected to show how to determine the forces in the members of a truss using two methods, the method of joints and the method of sections. And secondly, be able to analyze the forces acting on the members of frames and machines composed of pin-connected members. Now, what is a truss? It is a structure composed of slender members joined together at their end points. Commonly used are wooden struts or metal bars. Now, particularly, planar trusses lie in a single plane and are often used to support roofs and bridges. Now, the figure in A is an example of a typical roof supporting truss. And in A, the roof load is transmitted to the truss at the joints by means of a series of purlins. Now, since the loading acts in the same plane as the truss as provided in figure B, the analysis of the forces developed in the truss members will be two-dimensional. Now, there are examples or there are lectures for three-dimensional analysis for truss, but it will not be covered in this lecture video. Now, roof and bridges are mostly the applications of truss. Now, in the case of bridge, as shown in A, the load on the deck is first transmitted to stringers, then to the floor beams, and finally to the joints of the supporting side trusses. Now, just like the roof truss, the bridge truss loading is also coplanar, such as in B. Now, when bridge or roof trusses extend over large distances, a rocker or roller is commonly used for supporting one end, and for example, that is in joint A. Now, where is that? It's here. This type of support allows freedom for expansion or contraction of the members due to a change in temperature or application of loads. Now, just a heads up, we will not be covering the portion on the change in the effect of the change in temperature or the effect of the application of loads in terms of the expansion and contraction of materials, because that will be covered in mechanics of materials or strength of materials. So for now, we will just know how to calculate the forces that will manifest inside each of the members. Okay, now there will be assumptions for us to have a much easier calculations or much easier way to solve for the members that the forces that will manifest in each of the member. Now, 1, all loadings are applied at the joints. So there will be no forces that will act in between the members. It has to be that all of the loadings, all of the forces will be applied at the joints. Now, in most situations, such as for bridge and roof trusses, this assumption is true. Frequently, the weight of the members is neglected because the force supported by each member is usually much larger than its weight. However, there is however, that is, if the weight is to be included in the analysis, it is generally satisfactory to apply it as a vertical force with half of its magnitude applied at each end of the member. Meaning, for example, this one. If you can notice our figure A, there is a car in the middle of AC, and that car weighs 2,000 kilograms. Now, if you convert that mass into weight, you just simply multiply that with 9.81, or the gravitational acceleration. So we will have the weight. Now, of course, by virtue of what we have learned so far, it has to be that the weight should be applied here. But under this assumption, we will be dividing our calculated weight, because again, it has to be that the loadings must be applied at the joints. So whatever the weight being calculated here, we will be dividing that, and we will apply the divided weight at the edge of that member, which is, for this case, at A and at C. For this case, so half of the weight would be 4,905, the other, which is applied at A, and the other half will be applied at C. Okay, so that is the exception. Okay, but still, it has to satisfy this assumption that all loadings are or must be applied at the joint. Okay, next assumption would be that members are joined together by smooth pins. So basically, it means that our members here will act as two force members. So there will be an X and a Y component. Okay, now because of the two assumptions provided a while ago, each truss member will act as a two force member, and therefore the force acting at each end of the member will be directed along the axis of the member. So if the force tends to elongate the material, then it is a tensile force. Whereas if it tends to shorten the material, it is a compressive force. In actual design of a truss, it is important to state whether the nature of the force is tensile or compressive, because when that member the force that will manifest inside that member is compression, the design must be made thicker than tension members because of what we call buckling or the column effect that occurs when a member is in compression. But again, the amount of deformation or the amount of buckling or the amount of column effect that will manifest once the force is calculated will be covered in mechanics of materials. But again, for now, the most important part is we have to know how to solve for the force that will manifest inside the member, not the corresponding deformation because of that force. Okay, next. So we have been talking about tensile, compressive, and then all the assumptions. So let's move on to the actual method of solving the forces that will manifest inside each of the member. For our first method, we call it the method of joints. Now, in order to analyze or design a truss, it is necessary to determine the force in each of its members. One way to do this is the method of joints. This method is based on the fact that if the entire truss is in equilibrium, then each of its joints is also in equilibrium. Therefore, if the free body diagram of each joint is drawn, the equilibrium equations can then be used to obtain the member forces acting on each joint. Since the members of a plane truss are straight two force members lying in a single plane, each joint is subjected to a force system that is coplanar and concurrent. which means that only summation of forces x and summation of forces y is equal to 0 need to be satisfied for the equilibrium. So that is method of joints, concurrent coplanar force system. So this is an example here, A, B, and C. Now, for example, for pin at B here, we have three forces acting on that, namely the 500 Newton force which is going to the right, and the forces exerted by members BA and BC. Now, here BA is pulling on the pin, which means that member BA is in tension. So again, if you guys would forget whether it's tension or compression, one thing that you should remember is if it is away from the point, it's tension. If it's directed towards the point, that's compression. Now, when using the method of joints, always start at the joint having at least one known force and at most two unknown forces, because again, we will be generating two equations from summation of forces x and summation of forces y is equal to 0. Two equations. So you can only have at most two unknowns. If more than that, then you have to move on to another joint again to satisfy two unknowns for that for the two equations. And also, whether you satisfy two unknowns, two equations, if you are not given at least one known force, you can never solve that two sets of equations. So again, you have to satisfy this, at least one known force and at most two unknown forces. Now, you might be wondering, we do not know, or how do we assume the direction of the forces that will manifest in each member? Now, the correct sense of direction of an unknown member force can, in many cases, be determined by inspection. In more complicated cases, however, the sense of an unknown member force can be assumed. Then, after applying the equilibrium equations, the assumed sense can be verified from the numerical result. A positive answer indicates that the sense is correct, whereas a negative answer indicates that the sense shown in the free body diagram must be reversed. Simply put, for example, this one. At B here, there is going to the right, which is 500 Newton, and then we will have two forces. Force BA, still, if you can notice, I did not put an arrowhead yet, because we'll try to inspect whether BA is indeed tensile or is it compression, or BC is compression or is it tensile. So we'll have two forces here. So again, BC also doesn't have an arrowhead. 45 degrees. This is point B. Now, 500 Newton is going to the right. Again, it has to maintain your thrust, your structure has to maintain equilibrium. So it must be that there is a certain force that will counteract the 500 Newton going to the right. Now for your BA, if you can notice, your BA is vertical. So it's either up or down. Your BC, on the other hand, has two options. It can either be going up to the left or going down to the right. Right? Now, it simply means also that BC is the only force here acting at point B that has two components, X and Y. Now for this case, 500 is directed along X, which is going to the right. So to maintain equilibrium, it must be that your BC will have an X component to going to the left. So for this case, your BC is towards B, which is going up to the left, and the X component or the left component of your BC is the force that will counteract the 500 Newton force acting at B, which is going to the right. So BC here is compression. Now, since we have established already that BC is going up to the left, now your BA, we have to assess BA. Now, since the vertical component or the Y component of your BC is going up, it has to be that there is a force that will counteract that going up force, which is your BA. So your BA now will be going down to counteract the Y component of your BC. And that basically is what it means when you do inspection for the sense of your forces. Now, of course, there will be instances wherein it is difficult to assume assume the direction of your unknown members. So it is widely accepted that if you are unsure as to whether that force is indeed tension or compression, meaning you cannot do inspection at that joint, it is safe to assume that all the unknown forces will be tensile. So that's the safest way to do it. Now, if this is done, then the numerical solution of the equilibrium equations will yield positive scalar for members in tension. Meaning, simply put, your assumption is correct. Now, and negative scalars for members in compression. Your assumption that that force is tension is wrong, meaning that the correct direction for that force is towards the joint, not away from the joint. Now, once a known member force is found, use its correct magnitude and sense on subsequent joint-free body diagrams. What this simply means is, if you can notice, you started solving at joint B here, so you were able to calculate BC and BA. So after this, since you were able to get the correct sense of BC, which is towards the joint, so if you do force summation at C, make sure to follow the correct direction of BC, which is towards the joint also. Okay, that's simply what it means. Okay, so these are some important points that you have to remember. And the procedure for analysis, this is the widely accepted procedure, but if you're able to look for procedure that is best suited for you, provided that it is logical and mathematically correct, again, I would accept that. But if you were not able to find those procedures that is best suited for you, this is the way to do it. Okay, so right after this is just the first lecture video because we're able to tackle method of joints only. Then after this, there will be series of examples, and then after that series of examples, we'll have method of joints, another series of method of sections, and then another series of examples. Then we'll have truss. We'll have frames and machines, and another set of examples. Thank you.